last year?
Kinda. So actually, what happened in mechatronics last year was that the school's server stopped letting me upload to it, and I am now totally free of the school server. I just host it on GitHub, my page. So it's up a lot more now, but I don't have. What I did was I upgraded Ruby on my machine for a different project, which is Ruby is what powers Jekyll, which is a templating thing that make web pages. So that's how I write my code to generate the website. So anyways, it broke all of it. Like at one point, it wasn't even up at all. Now most of it's up, but there are a few pages that are up down. So I got to figure out what's up with that. I kind of know. I just have to fix it. So we're going to do an example today, and gonna have to try to move relatively quickly because I'm going to try to write an entire Matlab script that solves it in Matlab and also do it all on paper as well, analytically. So we have a feel for how to do each way. So I think this will help you immensely with your homework. I'm going to do a problem from the chapter that's not assigned to you, but is a quality problem. So it says to transform this system, gives you the state equation. What's the order of the system? How do we know what the order is?
Because your x right there is 2.
Yeah, number of state variables is equal to the order, right? So 2 state variables, so it's order 2. Okay. And so we want to convert this system to a diagonal form and find the homogeneous response to these initial conditions. So let's go ahead and do that. I am going to do it from scratch.
What notes are we currently on?
So this is actually, the one that I had up there was a Mathematica notebook for the example. I added a new example this year, and I've called this one Note Set 5, but the other one was called Note Set 5 as well. I left it up there on this site, so they're both called Note Set 5, which is kind of confusing, but they're just both examples of similar problems, but they're different. And I'm going to upload the Mathematica script's still up there, so you can print it off, or you could download it and play with it in Mathematica, and the computer's downstairs. It's really fun. But I thought that this was probably a little bit more useful for you guys to do it by hand and in Matlab. So I'm going to do both.
Did you know that all your notes are like, there's like 404 errors for every single notes?
For every single one?
Every single one.
Okay. I'll fix all of that then. I don't know what's up with that. Okay. I will fix all of that. All right, so let's go ahead and begin. So we need to find the eigenvalues and eigenvectors first. So sometimes this is called the eigendecomposition when we're finding the eigenvalues and eigenvectors that will give us the diagonalized form of the system. So let's do that. First thing is to find the eigenvalues. So let's find the eigenvalues. Eigenvalues. So do you guys remember the formula? Determinant of, we use lambda in this one, but it doesn't really matter. Actually, in my notes I used s, but yeah, it's really the same. So determinant of lambda I minus a equals 0. This gives us our characteristic equation, and we can solve for the roots of it, which are the eigenvalues. Okay. Now let's go ahead and plug into this formula. So determinant, I'm going to have to move it to the left a little bit here. Determinant of lambda I is going to be lambda along the diagonal, lambda, lambda, and then 0, 0. we chose an identity matrix that's 2 by 2. Why do we do that?
Because A is 2 by 2.
Yeah, exactly. So we're about to subtract A, so we can't have anything besides a 2 by 2 there. A is negative 2, 2, 2, negative 3. A little cramped there. Okay. Now let's do that subtraction step first, just to take everything slowly. So we have determinant of. Now we just have one 2 by 2 matrix. The first element is lambda minus negative 2, which is lambda plus 2. The second element is 0 minus 2, which is negative 2. The 2, 1 element is 0 minus 2, which is negative 2. And the 2, 2 element is lambda minus negative 3, or lambda plus 3, equals 0. Okay, so what is this determinant? Recall that for a 2 by 2, it's very easy to compute. This term multiplied by this term, and subtract this term multiplied by this term. So we have lambda plus 2 times lambda plus 3, and we have minus what?
Negative 2 times
4.
negative 2. So 4.
So 4. Very good. Equals 0. And this can be rewritten as lambda squared plus, there's 2 lambda and a 3 lambda, so 5 lambda plus 6 minus 4 is plus 2 equals 0. Okay, so solving this, quadratic formula or whatever, lambda 1 and lambda 2 are equal to negative 0.438 and negative, actually I'm gonna switch the order of these, sorry. I'm switching the order because I'm prescient and know which order Matlab's going to choose. Because I did this I did this last night, or yesterday actually, and I tried to upload the video last night and it wouldn't upload. So let's do it in this order just to make sure that we come out consistent. Yeah, I mean the order doesn't really matter that much. So I'm calling lambda 1 negative 4.56 and lambda 2 negative 0.438. Okay, and those are our eigenvalues, so that part's done. Now we can find our eigenvectors. So eigenvectors. And did I underline? No, okay, good. So remember that the eigenvector problem, so if you can't remember the formula, you could just flip back in your notes to the formula that we plug everything into. Or you could just remember, as I typically do, that if you scale an eigenvector by lambda, by its eigenvalue, it's equal to the A matrix multiplied by that eigenvector. Okay, that's how I usually remember it, and then I derive the formula because I can never remember which formula I need. So, well, actually, I can often, but you guys might find yourself in a situation where you don't remember. You're on an island, you don't have your notes with you. So you've got lambda I minus A times M equals the 0 vector. And we're just going to plug the different lambdas in and figure out what the M's need to be. But actually, this lambda I minus A, we already computed lambda I minus A for this determinant, right? So I'm going to cheat and just reuse this expression for for lambda I minus a. This is just, oops, whoa. This is just lambda I minus a. And we've already computed it, so no point in redoing that. So we'll do that for each value of lambda. So lambda 1 equals negative 4.56. We're going to compute the eigenvector. So all we need to do is plug in lambda 1 here, which is the same as plugging in lambda 1 into this expression. Just get rid of the determinant, though. We don't want the determinant, and we want an m here. So it's not the same equation, it's just the same matrix. So using that matrix, we can say that negative 4.56 plus 2, negative 2, so I'm reading off here, negative 2, and then once again, negative 4.56 plus 3 has to equal, times m, right? So this is going to be m1 corresponding to lambda 1. So we'll call it m11 and m21 are the two values. That has to be equal to the 0 vector, which is that, represented that way. So let's, we can choose, recall that we can choose either the first row equation to do this or the second row equation. We should get the same result. So what I like to do is use the first row, find my eigenvector, and then plug it into the second row. It better satisfy the second row too. That's a check. So let's do that. So in the previous example that I did, I used sort of like, oh, well, it's a nice round number and you can tell what cancels what. Let's do it a little bit more systematically this time. I think that, on an exam, that can be very helpful when you don't see it, right? So this first row actually is an equation, right? So let's write that equation. It says that m1, negative 4.56 plus 2 is negative 2.56, good. m11. And then what's the next term?
Minus 2 m21.
Very good. Minus 2 m21 equals 0. So that's my first equation. I can't solve this uniquely, right? But I can solve for how these two variables are related to each other. And from this, we can see that solving for m11, we can see that 2m21 divided by negative 2.56 is equal to m11, right? I just solved this for m11. I added this term over and divided by negative 2.56. And we should compute what this is. So, do you guys know what that is? So it's 2 divided by negative 2.56. I'm rounding here to 3 significant figures. I'm doing that, maybe we actually have parameters and we know all of our parameters to 3 significant figures, but potentially we don't. Typically in these problems, I would recommend not rounding at all, but I'm doing it just to show you guys concrete numbers here at every step. Usually I don't plug numbers in until the very end, as you know, but I'm trying to be a little bit more helpful in some of these problems. So negative 0.781, negative 0.781 m21. So we know what our eigenvector is from this relationship, and we can write it down. So let's do that. So from this, we know that we know that m1, our eigenvector, is equal to any scaling. So I'm going to put alpha there to remind us that it's any scaling, because an eigenvector can be scaled by any number and still be an eigenvector. So if you plug in, you can plug in any number you want for m21. I like to plug in 1 because it's easy. So let's say m21 is 1. So m11 has to be negative 0.781 times 1, which is also just negative 0.781. Great. Eigenvector. However, if we were feeling like maybe we should check that, we can just use the second equation. So check. Negative 2 times m11. So let's plug in m11, which is negative 0.781. Plus, what is this? This is negative 1.56. Well, I'll do minus 1.56 because it's negative. Times m21, which is just 1. And does this equal 0 is the question. And if you do this calculation, you guys can just trust me. It is good. Now, we did some rounding here, so it might be like 0.001 or something, but that's a good check. The reason that this solution satisfies both is that they're not linearly independent, these two equations. So back in the day when you were solving systems of linear equations, you learned that they all had to be linearly independent if you wanted to have a unique solution. But this is not a unique solution, it's a family of solutions. My face is gone. Let's get it back. There we go. Okay. I like seeing myself in there. It's just, I'm kind of vain, I find.
Really?
Yeah, it's weird. Anyways, using a very similar procedure. I can't tell when you guys think I'm serious or when I'm not, but sometimes I say stuff like that and I just move on and I'm not sure if people think that I'm being serious or not being serious. So this is the second eigenvalue, right? And we can go ahead and do our plugging in. So this one is going to look just like this, except for wherever you see negative 4.56, we're going to be putting in negative 0.438. So I'm putting in negative 0.438 plus 2, negative 2, negative 2, and then I'm going to do negative 0.438 plus 3 times, and now it's going to be m12, m22 equals 0, 0. All right, so from the first row equation, we know that, what is that, 1.562? 1.562, if you add those together, times what? M12 minus 2 times M22 must equal what? 0. So we can solve this to find that M12 is equal to 2 divided by 1.
Should be a negative or a positive right there, right? Because it's negative 2 or minus a negative 2. Or no, sorry.
Oh, here we're just adding here because we're just using this first row
I was
equation.
thinking term or something.
Yeah, I think that's what you're. Yeah. Cool. 1.562. So it's 2 over 1.562 m2, 2, which is equal to, what is 2 over 1.562? About 1.28. So 1.28 m22. All right. So we can now write our eigenvector, which is m2. And we know we can scale it by anything, so I'll put a beta in there. You can scale it by anything you want. But we will choose m22 to be 1, again, because it's easier, which means that the m12 has to be 1.28. 1.28. Voila. And we could check, but I'll leave the check for you guys to do. It should also work on this other equation. Very good. Now, let's review the bidding. At this point, we have found the eigenvalues and eigenvectors, which it took us a few minutes. It wasn't super fast, but it was procedural, right? And our goal is to diagonalize the original system and then find the homogeneous solution. And the reason that we're doing the eigendecomposition and we're going to diagonalize is why? What's the key? Why do we do it? While you guys think, I will prepare my tea. Tulsi ginger lemon tea? What do you guys think? Why do we do it? Why do we need the eigenvalues and eigenvectors? So we found the roots, but they were to find the eigenvalues and eigenvectors, right? So we found the roots of the characteristic equation. That was to find the eigenvalues. What are we going to do with them?
To find the
Well, that's our goal, and the way that makes it easier, because we could recall that we could just go to the homogeneous or unforced solution is just the very special matrix that you guys will be able to remember what it's called in a second, I'm sure, times the initial conditions.
Diagonal?
No, but sorry?
Modal.
It's related to that, can be found from that. It's the state transition matrix, big phi. So the solution is state transition matrix multiplying the initial conditions, right? And we have the initial conditions, we just need the state transition matrix. But I told you that finding the state transition matrix is kind of hard unless you have a diagonalized form, right? So that's why we're doing this diagonalization, so that we can compute the state transition matrix from which we can get the solution, the homogeneous solution. Sorry?
Big phi.
Big phi. That's right. Which should be recognized as distinct from big Lee. Okay? Only a couple of you guys get my Trump jokes, but they're fun. I enjoy them. Okay. So here is my, so I've got my eigenvalues and eigenvectors. Let's pop on over to Matlab and see what they get. Okay. Well, let's write our modal and eigenvalue matrix. So our eigenvalue matrix, capital lambda. I have a hard time writing that because my pen smooths out. There we go. And that's just the eigenvalues along the diagonal, right? Lambda 1, lambda 2, and then zeros elsewhere. So we said that that's going to be negative 4 point something. What is it?
5, 6.
5, 6. And then 0, 0, and then negative 0.438.
Yeah.
Sweet. All right, so that is our lambda matrix. And let's write beside it the modal matrix, or the eigenvector matrix. I should make sure that looks like a capital. M is equal to, by definition, just all the eigenvectors put into the columns of the matrix, right? And we can do as many as there are. In this case, there are only 2. So we put them in. M1 is negative 0.781 and 1. And this alpha thing, we're just going to totally say alpha is 1, because we could choose anything we want. And actually, there are sometimes, so Matlab will use a different scaling than us, but they'll get the same answer. Or they darn well should. M2 is 1.28 and 1. So there's our modal matrix. Okay, so let's see what Matlab gets. So we bop over to Matlab, and we're feeling like we should probably clear everything and close all. And then we'll do, first off, it's just good form to start off with some parameters, right? So let's plug in our parameters. Parameters are A matrix is negative 2, 2, and then 2, negative 3. Don't worry, I'm going to upload this script. So, and the B matrix is 0 and 1. You're like, yeah. And then our initial conditions, these are all just given in the problem, right? The initial conditions are 2 and negative 1. So then we'll do the eigen decomposition. And the syntax is modal matrix, eigenvalue matrix equals eig of A, right? And let's just print that. Let's just see what it does. So there's our eigenvector matrix, our modal matrix, and here are our eigenvalue matrix. So they have the same eigenvalue matrix as us, but their eigenvector matrix, their modal matrix, is a little different, right? But it's the scaling difference. So they chose a different scaling for each of their eigenvectors, which will actually give them a slightly different result for their x prime variable when we get to the primed coordinates. It will be a little bit different, and we'll see where it's different. So we could, what they're doing actually is they're norming each vector. You guys remember what a vector norm is? It's the length of the vector. So they're saying the length of the vector should be 1, and they're choosing their norm based on that. So we could divide ours by the length of the vector, and we could get their values, but we're not going to do that because we don't have to. And I want to show you how, if you do it our way, you get a slightly different b prime and x prime, but that the solution is the same. Okay? So we're going to do that. So eigen decomposition. So that was super easy to do. Oh my God, my mocking is starting to turn into real life now. So state transition matrix. I see some shaking of heads, that's good. Let's do it analytically first. So in order to find a state transition matrix, we still have to diagonalize our system. Well, actually we don't, because we know that the A prime matrix is just going to be lambda, right? But the problem asked for us to diagonalize the system, so we should just go ahead and do it, because they just asked us to. So we'll do it. We'll do it, because we follow orders. All right, so diagonalize. So what is our, so our diagonalization is going to be that x prime equals m, no, that's not it. It's x equals m times x prime, right? That's our diagonalization transformation. And do you guys remember what happens when we do that? What happens to our A matrix? What's our A prime? I mean, the full thing is M inverse. I mean, we wrote this down before. M inverse times the original A times M. And do you remember what it came out to be? Lambda. Close to the identity. Diagonal. Lambda. So that's the diagonalized part. So we know if we use this, we should check this. Let's check that this happens in Matlab. So we'll define, we're going to define an M2 here. M2 equals what our eigenvector matrix, our matrix came out to be, which was negative 0.781, and what was the next one over? 1.28, and then the second row is just ones. So, and then our lambda was the same, so we can use theirs. So if we do m, so inverse m times the original A matrix times m, so this should work for m2 and it should work for m. So we'll do m2. Oh, I didn't evaluate this. I suppose I should do that. Okay, so we're getting a little bit of rounding issues here. It's not quite diagonal, but it's pretty darn close to diagonal, and it's pretty darn close to our lambda matrix. This is our first eigenvalue. This is our second eigenvalue. So that's good.
Diagonal would mean it has zeros on the other.
Yeah, these should be 0, but you see how there's some rounding
Yeah.
that's not quite happening. If we use theirs, they didn't do any rounding. So if we use their m, it should be real tight. So, yeah. So yeah, it's 2 times 10 to the negative 16. So it's super small. But even they have some machine precision that is nothing you can do. There's a, I think, is it chop? No, it's not in Matlab. I forget. There's a function that wipes away. It calls it 0 if it's below a certain threshold. Anyways, don't worry about that. Now, we've got... Oh, we lost my face. Hey. So we've got A prime being lambda, which is what we knew was going to happen, right? Then we also we need to compute B prime. We don't have to do C prime and D prime because we're only looking for the state solution and not the output solution. They are easy enough to compute if we needed them. So B prime is equal to M inverse times the original B. So computing M inverse, let's remember how to do that. So we'll I'm going to move this because this is going to take a little bit. I'm actually going to do the calc. Well, are you guys getting pretty comfortable computing the inverse of a 2 by 2 matrix? Yeah, and then you have to take the determinant and divide the whole thing by the determinant.
Just one more time.
Okay, one more time, but we'll do it quickly. 1 divided. So there are several ways to do this, but I'm going to do it by saying 1 divided by the determinant, which is negative 0.781 times 1 minus 1.28 times 1. All right, so that's the determinant. So 1 divided by the determinant multiplied by the original matrix with these two swapped, the diagonal ones swapped, so 1 and negative 0.781, and the other two with their signs changed, so negative 1 and negative 1.28. so that's our inverse, times B, which our original B matrix was 0, 1, way up here, 0, 1. So that is, we just have to go through this computation. Let's do it in Matlab just to, so we'll do a B prime 2, which means it's our by hand one, is going to be our M inverse, so M2, so inverse of M2 times the original B matrix, right? So we'll also compute the B prime for the eigen decomposition that Matlab got using a different scaling, which is totally valid. So we'll do inverse of M times B. And we're going to see something that we should pay attention to here. They're different, okay? But that's because our x primes are different. Because remember, the x prime is related to x using M. And if they have a different M matrix, I mean, it's just different by scaling of the columns, so they're very related. But it is different, so their x prime is different than our x prime. And that's why it comes out differently. But it doesn't matter because you can scale eigenvectors and there's no difference in the eigenvector. So our B prime from Matlab comes out to be 0.621, 0.621, and 0.379. Cool. So we've diagonalized, and that's enough. This is a description of the diagonalized system. Okay, now we can construct our state transition matrix. All right, so if we construct the state transition matrix, we want to know in the primed coordinates what it is first, right? Because that's the one that's easy to compute. So phi prime of t is equal to, do you guys remember what it is? It's always it's defined as the matrix exponential of, yeah, so a prime t, which in this case is e to the lambda t, which is easy to compute for diagonal matrices. So it's just the scalar exponential of each lambda. So lambda 1 t, 0, 0, e to the lambda 2 t. Okay? So that was easy. I mean, we don't even have to really, let's define it in Matlab. So state transition matrix, we'll do our analytic ones first. So phi, so we'll just do phi 2. Phi 2 equals, it's a function of time, and it is exponential of, it's going to be, so e to the lambda 1t. So lambda 1 in this case is L of 1 comma 1, the 1, 1 entry times t, 0, and then 0, and then x of L to, 2 times t. Good. So there is our state transition matrix defined. This is actually the same. It's identical to the one that we get from Matlab because their lambda matrix is the same as our lambda matrix. So I'll just call it phi. So phi is that. So easy enough. And now we want to compute we want to compute the output, right? Or I guess the state. So the state homogeneous solution. And so what we want here is x of t, which we know is equal to phi, we don't know phi, we know phi prime, of t times x of 0. Now, we do know how to go, we can actually, so we can go back and cheat and use the formulas that I provided earlier, or we can just derive it because it's actually kind of more fun that way. So let's say, what do you guys want to do? Yeah, we'll do it. Yeah, we can do it. Can we do it?
We're deriving it?
Okay, let's start out, we did it this other way before, so I'm going to do it this way. X prime of t, we know is equal to phi prime of t times x prime of 0, right? So one way to do this, I don't know, you could do it either way. Which way do you guys want to do it? I did it this way before. We'll do it this way. Okay, so we're going to say that this is, we know phi prime, which is great. It's phi prime of t times x prime of 0. Okay, so x prime of 0 we can get from x of 0 if we use this relationship here, right? So we just have to invert m and multiply by both sides, and we get that the x prime is equal to m inverse x of 0. Because we don't know what x prime of 0 is, we have to find it from x of 0 anyways. So we've got that, which is cool. And we could do that to find x prime, and we could find x prime, a solution for it, and that's great. But we actually care about x, right? And x is m inverse, so x prime is m inverse x. So I just changed the left-hand side of the equation, and I'll rewrite the right-hand side. Phi prime of t equals, or not equals, m inverse x of 0. And now I just need to solve for x of t, right? So multiply both sides by m. So I did this in the other lecture in general, so we don't have to do this every time, but it's kind of fun. So phi prime of t didn't go away. M inverse x of 0. So we now know everything in this formula, right? So what I did in the notes before, so if you're feeling a little bit confused, what I did is I derived this, and we said, oh, well, this is just phi of t, right? No, so this including the m's is just phi. So to convert from phi prime to phi, all we need to do is go through this relationship here. We need to use the m matrix. So I just re-derived it. I probably shouldn't have, just because it felt maybe confusing. But this is just phi. So we could go, there's a formula back in the notes that says, oh, phi of t is just this. So that's what I did. Anyways.
Because we started with x prime and we were trying to find it. And then the example we started with x and then went to x prime.
Oh yeah, you can do it either way. So in any case, all you need to know is that phi is equal to m phi prime m inverse. And you have m, right? You have phi prime. It was super easy to compute. It's just this. And x initial condition is given. And so your solution always looks like this. So if you are on a test and you're in a hurry, you don't have to do this derivation. You can just skip to this last formula, right? This formula is one that I would recommend having handy. Woo!
So the
That
m and the m inverse don't cancel out.
No, because they're,
Because you're multiplying them in a different word.
if they were multiplying directly, then they would. But they both multiply phi prime, so they don't. And remember, you can't switch the order of matrix multiplications. Yeah. So this is called a similarity transform, and it has some special properties that you might learn about in linear algebra, but I'm not going to go into it. Because we're out of time. However, let's finish. Let's finish. Okay, we can do this. Oh, if I can breathe. Woo! Okay. So, solution. We want to, the one thing that's a little tough is that our phi, we need to know phi prime at every, sorry, this is phi prime, right? Yeah, phi prime. So I'll put an underscore p. We need to know it at every value of time. That's a matrix at every value of time. So that's like a three-dimensional array, right? So instead of doing that, what I'm going to do is I'm going to compute what the output is at every value, or what the state solution is at every value of time, which can just be an array. So let's do, or a 2 by whatever array. So let's do that. So I will define a t vector, and it's going to go from 0 in increments of 0.05 up to 10. And I'll define, I'll pre-allocate an x solution vector, which is going to just be, I'll just do nans times 1s. And if you want to make your script so that you can change what the initial conditions are, you do length of x0 by length of time. So I'm going to get a 2 by however many time steps array out of this, right? And then I'm going to do a for loop. So for I equals 1 to the length of the time vector. So for each value of time, I'm going to evaluate the solution. So x solution value. So both rows and the ith column is going to be equal to. So it's going to be m times phi p of t. Or what is it? It's t vec evaluated at I. It's that time value. Times the inverse of m times the initial condition, right? The initial condition is x0. And that should populate. So now all we need to do is plot it, okay? So I'll do a figure, I'll do plot, time vector, and now I need so time vector and x solution value, or sorry, vector I called it. Vector. Both row, well, I'm going to take the first row, all columns. That's going to be x1. I'm going to make that blue. Hold on. And then I'll plot the second row, which is x2, and I'll make it red. And I'll do a legend x1, x2, and let's see if this runs. Oh, I gotta capitalize the n. And define variable t. T. Aha! Good call. inner matrix that dimensions must agree. So what is the size of this? We never evaluated that. Oh, it's 2 by 2. That's what I thought it would be. Okay, good. No, these all should match up. So this is, so can I do m times that? Yeah. And can I do, oh, I know what I did. This should be a column vector. The initial conditions, of course. Nice, but I also have this weird thing where I have to, it scales strangely on these screens, so I have to do a subplot 2 to 1, and then it'll show up so you can see it. What? Subplot, oh, I know, I did that at the wrong spot. It's never the computer's fault. Aha! Dang, right? We're looking at the solution for x1 as a function of time in blue, and the solution for x2 as a function of time in red, given the initial conditions 2 and -1. So yeah, they start at 2 and -1, and then they respond, and they go to 0.
Like, could you relate that to like a physical system? Like, what would that?
Yeah, so it's like if you had trying to think of a mechanical system. You had a mechanical system with second order, but not, so an overdamped mechanical system with two, an overdamped mechanical system. So one could be like the force in the spring is x1 and the velocity of the mass could be x2. And you have some initial velocity of the mass and some initial force in the spring. So say like 2 meters per second is the velocity of the mass, and -1 Newton is the force in the spring. Then this is how they respond. It's overdamped, so it's not going to oscillate. They'll just respond, and then they'll come to an equilibrium. Yeah. Yeah. Pretty sweet. And the script that I upload, it's got a few more tricks in there that I show you a few more things.
So, we did like the diagonalization was in there in the midst of the things we did to get to this point. I thought that was like solve other variables that aren't in the state equations.
Yeah, so that's why we had to do this transformation back at the end.
That's why we did that to get.
Because we could find x prime, and actually in that script, I show you how to find x prime and how to find x. So, but we usually care about the original x more than we care about x prime.
Which is the x is what we just graphed, and x prime would be the other variables.
Yeah, so x prime are the variables that, so we can find x prime by just taking that x solution and multiplying it by m inverse. And we would get that. So actually we could do that. So if you multiply this by m inverse, all you do is undo this m multiplication, right? M inverse times n. So if I take this out right now, and we do this, it's going to be the x prime solution, okay? So that's the x prime solution.
But now what are those variables, x1 and x2?
So these are x1 prime and x2 prime.
So like if you had mass and the velocity, or force and velocity, what would they just be?
They're probably not anything physical that you could relate to.
Okay.
And that's why we want it in terms of the x variable. And so we can do that last transformation of m times it, and now we've got it in terms of x.
The x prime is what it is for like the math portion. Doesn't really actually do anything for us in terms of the physical state.
That's right. We rarely want to stay in x prime. I mean, you could. I mean, that's the thing. You can go back and forth. So if you need it to compute the state transition matrix, it's convenient to go to prime. But then when you want the final solution and the values plotted, you want it in x. So, Yeah, thanks for sticking around an extra few minutes, guys. I know that it's Friday and you guys want to get out of here, so have a good weekend.